So what we're gonna do today is to learn about fast Fourier transform, which is one of the very influential algorithm I mentioned last time. Okay, but like one of the motivating problem that you can use fast Fourier transform to solve it is this problem. So let's look at this toy problem. Suppose that I give you two sets, right? It can be multi-set. So the first set have this element 2 and 4 and 4 and 6. And the second set T has like 1, 3, and 4 as elements. Okay. So now suppose I ask you, how many ways can you add a number from S, like pick one number from S and pick another number from T and add them to get 7? Can you tell me how many ways? I think it's like there are like 3 ways, right? Yeah. You can choose this pair, and then this pair. So that's 3 ways. Okay. So this is easy to check when the problem is small, but like can you do this quickly? That's the question. One way to do this quickly is actually to compute a polynomial multiplication. So let me try to model this problem as a polynomial multiplication problem. One way to do this is like this. I'm just given S, right? Given S here, I just look at each element here, and then I create like a polynomial. Like from S, I create a polynomial A. And so I just do it like this. Like if this is 1, 6 here, I put x to the 6. If there are two manifolds, then I make like a x to the 4. But there are 2 of them, so there are 2 here. And then do it for 2 here. Okay. And just do the same for B, for like another set T, and I get B. All right. So that there are 2 polynomials here. And now let's see if what will happen if we multiply these 2 polynomials, A multiplied by B, and I get C. So we can try to multiply them. Actually, I want to ask for 7 here. Okay. And we have learned this from high school, I guess, how to multiply 2 polynomials. So what you can do is that you can first multiply x, just take one term from B, multiply to everyone here, right? And what you're gonna get is like the first line is, well, this line, like you multiply it by x, everything here by x, so you get x cubed plus 2x to the 5th and plus x to the 7, right? And well, and then you're done with this term. Then just do the same for the next term in B. Multiply them, get the next line, and continue to the next line. So this is like you do it 3 times like this, and then you sum all this guy up, right? And when you sum it, you get this one. Everyone is good with this? Okay, yeah.
Isn't this just the same number of operations as if you were to try adding every single value?
Exactly. Yeah, this is really like you can see that this is really like kind of do it for every pair of number. Like you take one number, and this is like a one pair, another pair, and another pair. So you take like kind of for every pair of number in the two sets, you spend constant time. So that's like n square operation when the size of this polynomial is of size n. Okay. Okay. And now, okay, you get this polynomial, but you can observe that if I want to know how many ways can I get number 7 from from these two sets, I can also look at the coefficient of this polynomial c, the coefficient of x to the 7. It's going to be exactly 3, like the number of ways to add them to get 7. Well, because you can see that the way that you get this guy, right, for example, is from this pair, and the way you get this one is just from this pair, right? So then they add up to 3 here. These two, like there are one way to get 7, another 2 way to get 7, and then they add up to 3. Okay. So I gonna just define ci here to be the ith coefficient of polynomial c. That is, ci is just the coefficient in front of x to the I. And I hope that from this example, you are convinced that if you want to count how many ways can you add two numbers from the set S and T to get I, you can just look at ci, right? That's the so if you can multiply polynomial fast, then you can solve this toy problem easily. Okay. And so okay, now we know that okay, at least polynomial multiplication seems useful. It can be used to count these things. From the homework, you will see that there are many other cool applications of polynomial multiplication to solve something that, like, superficially it doesn't seem irrelevant at all, but you can use it. Okay. And that's the goal for today's lecture. You're gonna see at least how to multiply two polynomials fast, and like really fast using fast Fourier transform. Okay. So the problem that we're gonna look at today, is polynomial multiplication. So formally, what's the input? Basically, is a set of two set of numbers, a0 up to an-1, b0 up to bn-1. These are just the coefficient of two polynomials, right? The a's, the ai's, they are just coefficient of a. The bi's are coefficient of b. Right? And I'm going to just assume that n is the power of 2, just so that we can. This is easy to assume, because if n is not power of 2, you can just increase it a bit and the one that you don't just add, just set some ai to be 0. Yeah. Okay. So n can be power of 2. Okay. And what we want to compute is you want to compute a multiplied by b. Okay. So what we're going to show today is that you can, if these two polynomials, they are polynomial of degree n-1, then I'm just going to show you that you can multiply them in time, something like n log n. Okay. So quite fast, like it's almost linear. Yeah. So we're going to multiply this using n arithmetic operation. This arithmetic operation, it turns out it's gonna involve some complex number. I will recall in when we get to this. Yeah. But before going to this algorithm that use fast Fourier transform, the cool algorithm that we can learn today, we're gonna kind of work our way through it. First, let's at least convince ourselves that we do have n square algorithm from high school. It works. And then let's change our perspective and get another way to solve the problem using dy and conquer. At first, it's going to give you some bad, you don't get any improvement. It's just n square algorithm as well. But then with one insight from Karasuba, you can improve n square to something like n to the 1.58. So that's not the best. And at last, we're going to see how to improve it all the way to n log n. Okay, so that's the plan. Okay, so first, let's recall again the high school algorithm that we did here, right? Here I kind of do it when there are not too many terms here, right? But suppose that the degree of both polynomial here are at most n. There can be n many terms in each of these polynomial. I hope you are convinced that this algorithm will work for any polynomial, but the running time is gonna be n squared, right? Because you spend kind of n time per line, and there are n many lines, and then you add them up at the end. So it's n squared time in total. Okay. So that's not good, but at least it works. But now let me ask you one just kind of small digression. Instead of computing the whole polynomial c, this is n squared time to compute the whole polynomial c, right? But what if I just want one single coefficient of c? So c is the sum of ci, right? Ci x to the I. Suppose that I give you given I, just one fixed I. How fast can you compute ci? Just one ci. Any ideas? Yep.
Is it still O of n squared because you still have to go through every pair of coefficients basically?
Well, actually, you can do better. Maybe just stare at this algorithm. Suppose that I just kind of want to compute a one single coefficient. What can I do? Yep.
Is it order of I? Because you can start at 0 and I, and then look at the terms and then work inward and look at the sums between them, between the two sets.
Good. Very good. Yeah. What's your name again?
I'm Guy.
Guy. Okay, good. Thanks, Guy. So you said that you might just need order of I. Yeah. I can be as big as n, so in the worst case it's order of n. But very good. So what you say is this. What you basically say is that suppose that I want to compute ci, right? So how do you get ci? Ci could be, it looks like this. Ci you can actually write down that it's going to look like a0 times bi plus a1 times bi minus 1 plus a2 times bi minus 2 and so on, right? AI times b0. So you can just see that this is how the ith coefficient of C is. You can just write it down like this, because they just this is how you pair up the coefficient and you get the ith degree of C, right? There are these many ways to do it, and there are just I plus 1 many terms here, so it's order of I to compute this thing, okay? So this is this takes order of I, which is at most order of n operation. Okay. So yeah, in the worst case, it takes n time. If you just want one coefficient, you can get it in order of n. Okay. But so here I just rewrite it in using sum. I just rewrite this thing using in this way. Okay. So each of Ci you can do it in n operation, but if you want to compute the whole polynomial C itself, there are n many coefficients, and so you might need n square total operation still. Okay, you have.
So maybe this is a dumb question,
No.
but how would you would you have to assume that the polynomials to start with are sorted because you're taking the last one and the first one and then this the second one and the second to last one?
Yes. So I really say that my input is just this list of numbers.
Okay.
This is how I represent my two polynomials. The input is given in this way. And so you can just you can assume that it's sorted. Yeah.
So this is a question. So if we're taking n to be the size of the sets, since we've talked about how multiplication isn't actually order of n with respect to the bit size. If the numbers, let's say we had a small set but with huge numbers in them, so the multiplication actually took almost longer than the set.
Good.
Do you sort of understand what I'm asking?
Yes. So what you ask is that, okay, what if the number is so huge? Then you might take a lot of time just to multiply one number. And this is why what I say in this class is that I just gonna count the number of arithmetic operations. Let's forget about that the number is big for now. Yeah. Yeah. So most of the time, you can assume that the numbers that you work with is something that you can store it in the integer in C++ and you do it in constant time. Yeah.
Can you explain the CI part again? I didn't quite understand why we're going. BI is going backwards and the A is going forwards.
Sure. So, you mean why is it the case that CI can be written in this way?
Yeah.
Yeah. So, well, CI is just the CI is a coefficient of x to the I in C, right? So okay, C is you have this is your polynomial C, right? And so now if you have A, which is, let's say it looks like x0, x1, sorry, a0, a1, a2, x squared, up to, let's say an x to the n, and b, let's say it looks like this. Okay. And now, suppose that I want to know what is, let's say I want to know what is C2. Okay. The way that you can get C2 is you ask like what is the coefficient of x2 in C. So you're gonna get degree 2 here by like either multiply these two together or multiply these two together or multiply these two together.
Yeah.
All right.
Thank you.
Sure. Okay. More questions? Good. So anyway, you can compute Ci in O n operations, but to compute the whole polynomial C, you still need n squared. So that doesn't really improve anything, but it's a nice observation to know that to compute one coefficient, you can do it fast. Okay. And one word, like one terminology that is useful for you to know is that like the problem of computing the Ci, where Ci look like this, which is exactly how the coefficient of when you multiply like the coefficient of the result of polynomial multiplication is like this problem is also called convolution. Is it like you might have heard this word many times, and like so basically polynomial multiplication and convolution are actually the same problem. So whatever you learn about from this class is basically about convolution, how to do convolution fast. Okay. All right. So now we know what to do, like what is the problem, but okay, let's try to get some algorithm. Like that is faster. Let's work our ways to the faster algorithm. And what we try to do is to use divide and conquer paradigm. So what is this paradigm? It's a paradigm where like that applies to so many problems, and that's like what we're gonna do like today and like next class is actually about divide and conquer. This paradigm is like this. It's like you're given any problem, and you just try to divide them so that the problem looks smaller, but it's again the same problem. So you reduce the big problem to the smaller problem, but it's the same type of problem, and you solve the smaller one. Okay. This might look like this might sound a bit abstract. You might have seen some example from your previous class, but we're gonna see more things today. But okay, so let's try to see at least an example of the bad divide and conquer algorithm. Okay. So what? And then we try to improve it. So let's start with like some divide and conquer algorithm, but it's not really an improvement. So maybe I try to write my polynomial a and b. Sometimes I don't write ax, but I just write a. Okay. So I just kind of write a in this way. So what I mean is like, maybe an example is good. Suppose that a looks like this, right? It's like a polynomial of degree 5. There are 6 terms here. Then you just like kind of divide them into 2 polynomial, 2 smaller ones. The first 3, I write it's like as a high. The last 3, I write it as a low. Then by dividing a high and a low, I can just write a as a high times x cubed plus a low, right? So having a polynomial of degree like n, you can kind of define 2 polynomial of degree around n over 2 in this way, very natural way. Okay, and can do the same for b. Okay, I can define b high and b low. So yeah, so these polynomials are smaller because they now have degree like n over 2 instead of n. So now if I want to compute a times b, what I can write it like this too, right? When you multiply a and b together, then you can write like a high times b high times x to the n, and so on. Just like expand the multiplication out, but like you have only a low and b low and a high and b high as your like think of this as like a sum coefficient, but yeah. So you can write like this. And just from this expression, you can say that like it suggests a divide and conquer algorithm already, because here you want to multiply to get one multiplication between 2 degree n polynomial. And this is on this side, but it just equals to this thing. But what does it look like here? This looks like you need to multiply these two together, this two, and this two. So this is like 4 multiplication of degree like n over 2 polynomials. So now you can see that it's the same problem, but smaller. This is how you do divide and conquer, like reduce some big problem to the same problem, but smaller. So, and once you have multiplied these four things together, what else you need to do? It's just like some addition between like you just need to add polynomials, and do some shifting. But adding polynomial of degree n trivially takes n time, right? So the other operation in total just take n operations. Okay, n arithmetic operation in total. So if you look at this, then it suggests an algorithm that like, okay, you want to multiply this, just recursively multiply these 4, and then like just do some shifting and some addition, and you get a recursive algorithm from here. Okay. So from here you can see that like the recursion, like if I now I hope that you are convinced that this recursive algorithm should work, just because we just really follow this this expression, this equation. And how should we let's try to analyze the running time of this recursive algorithm. So let Tn be the time from like the upper bound of the operation to number of operation to multiply this to polynomial degree n. Okay. So the running time would look like this. To multiply 2 polynomial of degree n, you need to do 4 multiplication, right? Just this 4 of degree n over 2, and at the end you do something like n operations to add them up. Okay, and you can see that like you can try to solve this equation, this recursive equation, and from like the master theorem you can see that okay, it's n squared, so no improvement, but okay, it's a different algorithm. Okay, by the way, like in this class many times, like I'm not like actually let me ask, how many of you have learned master theorems? Okay, basically everyone. How many didn't see it before again? Okay, so master theorem is like some quick way to solve the recurrence like this, and like there is like some just 3 formula you can look up, and then boom, just apply it and you get it. So just look up the internet and see it. But many times in this class, like a master theorem is just not enough. Like in last class, maybe it's enough. This class is not enough. And let me at least try to show you how to prove, how to solve this recurrence directly, right? There will be many ways to solve recurrence. Let me show you one way. like what we can do is like try to do this thing by hand. Okay, so so the way to look at this is like this. So you start with a problem of size n, and from the problem of size n, you're gonna recurse to 4 mini problems, each of size n over 2. And this guy, n over 2 here, is gonna recurse to 4 mini subproblems of size n over 4, like it keep halving its size, right? Okay. And you can imagine that like you have this big tree, like just like kind of the branching factor is 4, and like the size of each of this is like it's getting half and half for each level. Okay. So now what we need to do is basically we need to sum the number here together, because like you can see that when the problem is of size n, you pay n here, but the rest here you cannot put it in the recursion. So each of this one you spend O(n) time, each of this you spend O(n) over 2, and so on. So you have this big tree, and you basically want to sum up every number in this nodes, right? So how to do this? So let's try to do this level by levels. How many levels are there? It's gonna be like log base 2 of n, because each time n keep halving by 2. So when n is like a constant, it's like 1, then you're gonna stop. So the depth is like log n base 2. Base 2 because you halve it by, like you decrease n by factor of 2 in each level. Okay. And now like let's try to count the number of subproblems per level. The first level is 1, the second level is 4. The next one is like 4 square, the next one is 4 cube, and so on. Right. So like at depth d, the number of subproblems is going to be something like 4 to the d. Okay. So now what we need to do is just like try to sum up these numbers per level. Okay. So the time that you spend at depth d, like let's look at depth d, right? There's going to be like 4 to the d many nodes here. Yeah.
What is the depth of the tree? Is that log 2 of n or?
Log base 2 of n.
Oh, okay.
Yeah. Okay. So the time that you spend on depth d is like 4 to the d many nodes here on each node. Like there's going to be, let's say that this is like depth d. There's 4 to the d many nodes. 4 to the d. 4 to the d. And each of these is going to be like n over 2 to the d. So this is how it looks like. The total time you spend on depth d is like this times this, which is order of n times 2 to the d. And then you just sum them up over all levels, right? So the first level is O(n), the second level is like kind of 2n, and you sum up over log base 2 many levels. So the last level is like this, n times 2 to the d, but d is like log base 2. And you can see that this is a sum, but this is like basically a geometric series where the rate of this guy is like 2. It's like you multiply by 2, 4, 8, and so on. So when you sum up geometric series, what you know is that it's just the last term that dominate everything up to constant factor. So you can just look at the last term. What's the last term here? What is 2 to the log n? Is n. 2 to the log base 2 of n is n. So this is, just look at this last term, is n squared. Okay.
How did we get, I mean, this is a trivial question, but how did we get from n divided by 2 to the power of d to n times 2 to the power of d?
Oh, so this thing times this thing
Oh,
is this thing. Yeah, like good.
I was assuming the 40 was constant, that's why.
Right. Yeah. Okay. So it gives you n squared at the end. It's as Master theorem said, but like you see in this class, you need to do this kind of thing sometimes. Sometimes Master theorem is not enough. Okay. All right. So now, okay, it's not that great. You get some algorithm that is not faster. Okay, so now comes the insight by Karasubat. Okay. The insight is this. So we have seen this before, that a times b can be written in this way. There are 4 many terms here, 4 many multiplication here. However, the 2 guys here can be rewritten in this way. This way. What does it say? It says that suppose that you have computed, if you have computed this guy and this guy, and you must compute it, you want to compute them anyway. Suppose that you have computed these two already, right? Then you can reuse them here and just do one more multiplication. Instead of spending 2 multiplication, you just need to spend one more operation. So instead of 4, you spend just 3 multiplication to get every term. And this is the key insight. Before you start with a big problem, you need to reduce to 4 many smaller problems. And with just this expression, you can see that all you need to do is to compute just 3 many smaller problems, which is this guy, and this guy. These are the 3 guys that you need to multiply. Make sense? Just this reduction from 4 to 3 is significant. Okay? So this basic, like, yeah, just from this key insight, it just lead you to like a new algorithm immediately. How? Just compute like the A high times B high and A low times B low, and then compute the third guy here, right? How to compute the third guy? Just do some like a subtraction, and subtraction that takes n time is not thing, okay? And do multiplication. So there are 3 multiplications you need to do, and then at the end, you can just return this thing, which is what? It's just about addition, subtraction, and shifting, and that takes O(n), or order of n. Okay. So can you tell me how does so this algorithm will work? What's the kind of the recurrence of the running time? Can anyone tell me? How does it look like? If the running time is t of n, how does this recurrence look like?
3tn over 2 plus O of n.
Yeah. Right. Because now you just have 3 subproblems. Each of these is like a polynomial of degree n over 2, and you spend order of n time outside this recurrence, outside the recursion. So you improve from 4 here to 3. Good. So this is good, and So you can see that now it's like the same thing, like to multiply polynomial of degree n, you reduce to the same problem with 3 multiplication with smaller problem. So same problem and smaller. And everything else you just spend like order of n time. Okay.
What does the O of n represent?
Order of n here is like is for like to add and subtract polynomial of degree around n and to shift polynomial of degree around n. Okay. All right. So this is just a pseudo code, but I just gonna skip it. It's just the same as I explained. And this is the this is the recurrence, right? It's 3. T of n is 3 times t of n over 2 plus order of n. Okay. And okay, by master theorem, you're gonna get this, but let's do it by hand again. Okay. So I'm just gonna show you how to solve this by hand. Now instead of writing the trees, I can just try to do it algebraically too. So we can do something like this, right? So let's try to simplify this a bit. Like instead of write in order, just write n and pretend that there is no constant here. Okay? And what you can get here is like t of n is this thing. Okay. So what you can do is like just to, expand this thing out by one step. What is this thing? This thing is t of n over 2 is 3 times t of n over 4 plus n over 2. Okay. So I just expand this thing and I get this line. And then I expand this thing again, I get another line. Can do this by hand, right? And then if you keep doing this, like you're gonna kind of keep reducing. Like you can ask yourself, how many times can you keep expanding this thing until this is 1? It's going to be log base 2 of n again because each time you keep halving n. So the number of times that you keep halving is log base 2 of n. Okay, and you can look at the pattern here. It looks like n and t over 3 over 2 times n, t over 2 squared times n. Next one is going to be 3 over 2 cubed times n, and so on. So it's going to look like this. And there's going to be like a log base 2 many terms. Okay. And you can see again that this is a geometric series of red plus more than 1. So only the last term dominates. So just look at this one and then calculate it. Yeah.
Where does the log base 2 of 3 come from? How is that one derived exactly?
Because you keep halving n by 2.
Oh.
Yeah.
That's also the depth of
Yeah, that's the depth.
Oh, okay.
Yeah. All right. Okay, so this is just some calculation. You look at the last term here. The last term dominate, and you calculate it, and you get this thing. Okay. I'm not gonna look at this calculation too much, but yeah. Okay. So some of you might have seen these kind of things in previous class, but if you haven't, then just to make sure that you understand this, suppose you can try to adjust the same idea here to different problem. Let's say you want to different problem of like integer multiplication. Yeah. Suppose that you have 2 numbers of n bits. You want to multiply them together. Can you multiply them using just like n to the log base 2 of 3 bit operations? Yeah. Just it's going to be a very similar algorithm. Okay. Anyway, let's see let's try to reflect on what we have done, right? How did we get this improvement? You can see that both algorithms are divide and conquer. they both just reduce the problem of size n to smaller subproblems. But now the number of subproblems is 3 instead of 4. Okay. And that gives you like some very nice improvement already. And you can ask yourself, can you go further? Instead of like 3 mini subproblems, can you reduce it to 2? And if you can do it, then how would the recurrence of running time look like? It's gonna look like this. Like you have 2 instead of 3. And you can, if you know, like if you can try to solve this thing, you can see that this actually solves to n log n, which is what we want. So this is exactly what we're gonna do. We're gonna try to reduce the number of subproblems to 2. Okay. So this thing just solve 2. If you can do it, this thing would be n log n. But Karasuba idea that you just seen will not work. We need just like kind of completely new ideas. And to do this, we need like some background. Okay. So any question before I really now talk about the fast Fourier transform? Okay. So let me talk about some background here. So when you look at polynomials, right, we have so far how we represent the polynomial is just represented using its coefficient, right? If a polynomial has degree n, then I just say that okay, just list like the coefficient from a0 to an-1. That's just a list of numbers here. However, you can represent polynomial in different way too. Okay, because you can think of polynomial as a function. Like, for example, like if polynomial is x squared plus 1, then a1 is like a 2 and a2 is like 5, right? Yes. So you can like think of polynomial as a function, and you can actually represent it as a map, like as the evaluation point. Like given a point pi, and evaluate a at pi, and record that. Okay. Now, I claim that this is really a representation. In what sense? This is a fact that I would like just like assume, but I explain it. At least you try to understand the statement. Why is it the case? It's just from like a basic fact from algebra, right? So what it says is this. Suppose that I promised you that a polynomial a has degree n-1 at most. Now, if I take any set of points, n points, from p0 to pn-1, then like this like point value evaluation actually would determine a. If you have n many points, there are only like there is a unique polynomial that evaluate to this point, like to this thing. Yeah. For example, if I let at least see one example. If a polynomial has degree 1, so it looks like, let's say it's x plus 1. Okay. So how it looks like is like this is x. The polynomial looks like this, right? And then if I fix a polynomial, then if I say that I want to evaluate at point 1 and 2, then this is gonna look like point 1 and 2. This is gonna look like 1 and 2, and this is 2 and 3. Okay. These 2 points. But if I fix these 2 points, then it's gonna like that. It's only one polynomial of degree at most 2, at most 1 that fit these 2 points too. Right? If I say that, okay, I have 2 points here, then there is only one polynomial that would fit it. Okay, so okay, yeah. So basically, I can represent any polynomial as like a point value evaluation. Okay.
This is just to clarify. So if you have like a polynomial with like the highest degree of 7, then you would need a maximum of 7 points to determine the entire polynomial.
Yeah, right. If you have only 6 points, it's not enough. If you have 7 or 8 or more, it's gonna fix that polynomial completely.
The set of points is just a set of x coordinates because we call like A of pi.
Yeah. The set of points pi is like you can think of x coordinate and this is y coordinate. Yeah. All right. Okay. So I'm just saying, repeat again. If there are like, it means what? It means that if suppose that you have like a 2 polynomial a and a prime, and if someone said that like a and a prime somehow agrees on n many points, then it must be that a and a prime must be exactly the same polynomial, as long as its degree is at most n-1. Okay. By the same, exactly the same, I mean like the coefficient here, ai and ai prime, they are exactly the same for all I. Okay, so this is the fact that we're gonna use, and okay, so now the key insight is this. Suppose that when people like suppose that our input, right, instead of right now, our input is given in terms of coefficient of polynomial. If the input is actually given as like a point value representation of polynomial, let's say that I'm given this thing, the evaluation of A on point Pi and the same evaluation point of B on Pi. Okay. Then how can I compute the multiplication, like the C, A times B? Then it's gonna be easy problem. Why? Because I can just say that this is how C look like at point Pi. It just look like A Pi times B Pi. Just like just do this multiplication per each point. For each point. All right. So it means that I just take like just n multiplication here, and then I'm done. I get C. So what does it say? What does it say? It says that like the representation of the input matters, right? If the representation, the input is represented as coefficient, then it's not clear yet how to get multiplication. But if the input is given to you in this way, the problem is easy. Question? Yeah.
So are we saying that the polynomials are degree n, but we're given 2n minus 1 points
Yeah.
from those polynomials?
Yeah. Why 2n minus 1 point? Because like polynomial C might have degree something like 2n. Like 2n minus 1. So we need to have enough points to determine C. Okay. So this is like a good insight. But with this, then our strategy, the strategy is as follows. What we're gonna do is like, this is our input, which is the coefficient of A and B. We're gonna actually compute like a, we wanna get point value evaluation of A and B. Like try to represent A and B in different way by choosing some point set and evaluate them. And then once you have this thing, it's easy to multiply them. Just multiply the evaluation point-wise in n time. And then try to convert back to coefficient of C. That's the plan. Okay? So let's proceed. So all we need to do is to design like a special point set so that you can evaluate this A and B at this point set Pi in time n log n, and then do the reverse. Given like the point set evaluation of C at this point set, then try to get the coefficient of C. Okay, this step is easy. We just need to do these two steps here. So the rest of the lecture is about how to do the two step, the first and the last. The middle one is easy. Okay. Okay. So okay, let's try to do this. So by the way, like I said that I need to like define kind of two and many evaluation points. Let's try to like just for notation, like just to make notation easy. Let's, instead of deciding two endpoints, let's say I just like rename the parameter a bit, and I want to just design endpoints. Nothing happened. Just change the parameter a bit from now. Okay. And sometimes I'm gonna be a bit sloppy. Like there are degree. Sometimes polynomial A has degree n-1. Sometimes I just say n and so on. So just 1 plus minus 1. Sometimes I may be sloppy. Okay. Anyway, our goal is this. We want to carefully choose a point set to evaluate. Choose a point set P1 up to Pn so that you can evaluate this polynomial at this point fast. Okay, we want to do it this fast. So, by the way, just a quick question. Suppose that I have just one point and I have one polynomial. How fast can you evaluate it? How many operations? Yeah. Or order of n. It's kind of not hard to see. Like okay. If I want to evaluate this when x is like some point p, if you do it not carefully, but just do this like a term by term, it might take like for each of this term, it might take you like n operation already, and there are n terms, and that's n square, so that's bad. But there are faster way, which is actually let me set this as an exercise. How to evaluate ax at one point p in order of n time. How do you do this? Yeah, it's a good exercise. But you see, like just evaluate at one point. If you are clever, then you can get n. But here we're gonna design like n many points and try to do this in n log n time. One point you take n time. If you do it not carefully, you might take n squared to evaluate many points. But we're gonna see how to do it, like to do everything in n log n. So it's gonna be really cool. Okay. So this point will need to be like carefully chosen, actually. So let's try to let me try to tell you how to choose this point set. Okay. So what we're gonna do is like let's consider a new way to divide the problem. Okay. We used to like given a, we used to divide the problem into a high and a low. Now let's try to do it differently. I'm gonna define a even and a odd in the natural way. For example, like if a is like this, there are 6 coefficients, then a even would collect all the even coefficient, and a odd would collect all the like the odd coefficient, and the degree is like half. Okay. I hope this is clear, right? The definition of a even and a odd. And the observation is this. Here is a key observation. Suppose that I have evaluated a even at x squared and a odd at x squared. Okay. Then I can quickly compute ax. How? It's just a even square plus x times a odd square. You can just verify from here, right? If I put a even square, then this is like you get like if this is square, this looks like 4, and then I multiply everything here by x, then add them up together. It's just gonna give you a, the original a. Okay. So this is just nothing, algebra. However, the key insight is this. Suppose I have compute this too. I can, nothing surprising, I can compute ax. But the nice thing is that I can also compute a at minus x quickly too, by basically do nothing in addition to this. Because a at minus x is just, I just use the same thing here, and I just use the same thing here, and I just need to multiply by minus x here. Okay. Okay. So this looks like a nice thing because like there are like I can kind of get 2 evaluation points by like not doing, like I can reuse my information from here to get information for here, right? Okay, so now suppose I do this. Suppose I choose endpoint of evaluation to be like this. I have P1 and minus P1, P2 minus P2, and so on, right? So there are n many points. They are like a pair up, like a negation of each other. There are n over 2 many pairs. And then we're gonna evaluate a even and a odd on like the square of these things. The square of everything here, which is just like this guy and this guy square go to the same number. This guy and this guy square go to the same numbers. So at the end, I need to evaluate the point set that I need to evaluate on a even and a odd is just on n over 2 many points, not n, just n over 2. Okay. But yeah,
Why do you choose both the positive and the negative points?
you're gonna see it now. Yeah, like so the point is that I choose positive and negative now because the next step here, you can see that if I want to evaluate a at pi and at p of minus like a of minus pi, I can just kind of basically reuse the same thing that I have computed. So by choosing them to be like a negation pairs, I can compute these two numbers by reusing information. Like there is an efficiency of information here. Yeah. Right. Okay. So each of these, I have like in the first step, I have already compute a even and a odd at all of these guys. So this is, I have all of this thing, right? And to get these two guys, I just take like a O1 operation to multiply numbers here and add them, multiply the number here and add them and subtract them. Okay. So you can see that like this set of numbers, the set S of numbers here that have this negation pair, they have good structure. In what sense? In the sense that if I want to evaluate A at n points, now I just need to evaluate like two polynomial A even and A odds, which have degree half. At how many points? N over 2 points. It's n over 2 points because like the pair of negation, when you square they go to the same number. So they are just, you start with n points, you end up with n over 2 points. So now what you see is like you have one problems, you really reduce to this like two smaller same problems. And how many subproblems are there? Just two. Okay, so this is kind of what we want. We used to have 3 subproblems before, now you have 2 subproblems. Okay. So the recursion now looks like this, which solve to like a log n. But this looks good, except that there is something wrong with this argument. Yeah.
So S prime is going to be like a recursive set for the next step.
Yeah.
But isn't it not like because S, we wanted it to be like negative.
Exactly. So this is exactly what we are missing here. Like there is a bug in argument that I try to say. Yeah. The problem is exactly what you said. The structure of S is such that you have negation pairs, but when you recurse to S prime now are all positive. It doesn't have the same structure that we can exploit this recursion again. So we cannot continue. So it's not correct yet. Okay? But I hope this and that this is a very important point that we need to fix. Okay, I hope you understand this issue. Okay. So what we want to design is like some set of points such that when you square them, you kind of end up with a smaller set of size half. And then when you square them again, you end up with this kind of smaller set of size half, and so on. We want this kind of structure that when you square, you halve the size of the set, and this can keep going. Okay. And the point set that satisfy exactly this thing, it turns out it's gonna be the complex root of unity. So, okay. Before I go on, I want people to ask question. Is everyone on the same page?
So are the points at S that you pick, I mean, now we pick positive, negative to like take advantage of like the recursive nature, but are the points that you pick like arbitrary otherwise? Like
Previously it was arbitrary, like the point set that our negation pair was arbitrary. But we see that if we do it arbitrarily, then you cannot continue your recursion because the next point set x prime is just all positive and you cannot continue. Now we're gonna see that to fix this problem, all the point set, the end points here will not be arbitrary at all. We fix all of them, which is gonna be this root of unity.
so like one more question, I guess, like how does the identity where you have like n two polynomials with like a degree of n minus 1, how does like the identity like n shared points, I mean they're like congruent, like how does it relate to this, I guess?
Oh, you asked like how does the fact that evaluation points of polynomial determine a polynomial relate to everything?
Yeah.
Basically, it's just from here. What we're gonna do here is like to evaluate this polynomial C at 2n many points, and once you have that, it's gonna determine C exactly. Yeah, that's the. Yep.
Can you define A even, A odd again? I'm a little confused as how like if we square x square them, how do they result back?
A even and A odd is defined in this way. Like I have A, and then I just collect all the even coefficient, and then just kind of write it down as like a polynomial of half degree.
But when you have A even x, like A2x is A2x squared, but when you do the x squared, you do it as A2x squared as it is.
This is okay. I mean, so I'm not sure I understand your question. Like
for example, A even x, right? It's A0 plus A2x plus A4x squared.
Yeah.
But the equation is A0 plus A2x squared.
Right. Like so you have the degree. Yeah.
Oh, the degree.
Yeah. So in general, A even looks like this, right? A even looks like I even and 2i and then just x to the I.
Oh, okay.
Yeah. Okay. So what I'm going to do today is maybe like I might not finish actually now, but let me at least try to let you see how good this root of unity is, and then we're gonna finish the whole algorithm next time. So let's recall what is root of unity, right? Like when you look at x to the n equals 1, when you look at all the solution of this equation in the complex plane, it's gonna look like this. For example, if you ask about the nth root of unity, like what's the solution of x to the 8 equals 1? The first one solution is just 1, right? 1 to the 8 is 1. But another solution in a complex plane, everyone know the complex plane. Like you have 0 here, 1 here, minus 1 here, and another direction here, which is I minus I. Okay. So, like, there is another solution. Like, there are actually 8 many solutions to this equation, right? For example, this number that we call like the primitive root of unity. this guy. When you this is like the point here when the angle is like a 2 pi over 8. And then when you look at this guy, a square, it looks like this. You just kind of double the angle, you get this guy. When this guy cube, you just triple the angle here, and then you get this guy. So if you power this guy by 8, you're gonna do this 8 times, and you get to 1. So you can see that like this guy to the 8 is 1. Right? I'm just reviewing quickly what is root of unity. This guy also, if you multiply this by itself, it's like the angle will double, so you get to this. If you do it 8 times, how does it look like? It looks like this guy multiply this guy square, you're gonna get to this guy. Do it 8 times, you're gonna do this guy. 1, 2, 3, 4, 5, 6. Wait. One sec. I want to look at this guy. I to the 8 is what? Like you have 1, 2, 3, 4, 5, 6, 7, 8. So you get 1 again. So basically, for each of these points, when you multiply, when you power each of these points by 8, it's gonna go to 1. They are all root of unity, 8th root of unity. Okay. This is like the 4th root of unity. These are all the 4 points, such that when you